Okay, so I have put up the reading assignment and the homework assignment. There's the first project that's due on Monday. It's pretty simple. It's actually just using MATLAB or Octave, getting used to it. So I've got some videos on installing Octave. So on your personal computer, Octave is free. So you can essentially do everything that you can do in MATLAB. So you don't need to go out and buy MATLAB. Actually, I'd encourage you to use Octave. But this first project just has you do a couple of exercises in Octave or MATLAB. Okay. So I'll try to post a link to that video that shows how to install Octave and at least get started with it when I get up to my back up to my office. Please upload the homework to Blackboard. So the homework is due in here on Friday at 3. So make sure it's posted to Blackboard by then. Same with the project. The project is actually supposed to all be done in a word processor. I'm not sure if this first project has figures in it, but again, you can usually just import those from Octave into Word or whatever you use. Convert those to PDF and upload everything in PDF to Blackboard. Okay. Any questions on that? Okay, so I'm going to talk about probably one of the most confusing topics in electrical engineering today, convolution. And we'll try to work through a couple of examples. And we'll pretty much spend the rest of the semester looking at techniques that allow us to not do convolution. But in order to appreciate those techniques, you're going to have to do some convolution. So there are some problems in the homework where you do convolution. This is usually one of those things, often students have to see it a couple times before it makes sense. I mean, it's an integral, but it really forces you to have kind of a deeper understanding of integration and limits on the integral and what the integrand is. Okay, so for an LTI system, so last time we talked about the impulse response, H of t, the output, Y of t, when input is X of t is, okay. So the trick here, this applies to any system that can be described actually by a linear constant coefficient differential equation that corresponds to an LTI system. We can find the output of that system to any input. Okay, so it's really solving the differential equation. We can do that for any input using this technique. It's called convolution. The trick is somehow we have to get the impulse response, and that's not an easy thing to do. If you can get the step response, we can take the derivative of the step response to get the impulse response. But once you have H of t, we can calculate the output by carrying out this integration. H of t minus tau d tau. And this operation is called convolution. You can look at it just as a mathematical operation, okay, between two functions. It involves two functions of time or space. Okay. But to us, it has deeper meaning. For an input X, with input X to a system that has impulse response H, if we can carry out this operation, we can get the output. You can actually interchange x and h, and you get the same result, okay, for a linear time invariant system. So the notation we use, this appears so often. It's represented by an asterisk. Okay, so this is not a multiplication sign like you might see in a computer programming language. Anytime I write that symbol in this class, it represents convolution. Or equivalently, you can reverse the order there. So actually, what that means from a system standpoint, you know, if we've got a system with response h of t, impulse response, and feed it x of t, we get y of t. Well, if you build another system whose impulse response was this first input and fed it h of t, you get the same output. You can reverse the order of operations. Mathematically, what's that called? You remember the term? You can reverse the order in which you do the operation. I can't hear. You have to speak up. I heard some mumbling, but it didn't carry far enough. It's commutative. Okay. This is the general form. This is what we'll normally start with. There are some special cases that are common. If the system is causal, and that means that h of t is 0 for t less than 0. I don't know if we talked about did we talk about the causality of the system? I know we talked about the causality of a function, but a system is causal if its impulse response is 0 for t less than 0. Kind of what that means is we've got this system, we feed it delta t, we get out h of t, right? That's the definition of impulse response. Well, delta t comes along at t equals 0. You wouldn't expect any system to be able to produce an output before the input arrived. That's essentially causality. So h of t has to be 0 for all t less than 0. Okay. It might, once this impulse arrives, it might produce an output for a long time, but it can't produce an output before that input arrives. If it did, it would be a non-causal system. Another term for that is an anticipatory system. If it started producing an output at t equal -1 before the input arrives, somehow it's looking into the future to say, okay, I'm going to get an input in 1 second. I'm going to start producing output now. Okay, so now we can work with non-causal systems mathematically. Our only restriction is that they're linear and time invariant. Okay, but physically you can't build a non-causal system. I mean, it's essentially a time machine, okay, something that can see into the future. Now, it would be okay to actually not have a response until t equal 2 seconds, 2 seconds after the input arrived, right? It's okay to have a delay. You just can't have an advance. You can't produce an output before the input arrives. But if this is true, if h of t satisfies this condition, we'll talk about how to draw this thing and sketch this. But what that means is it changes the limit on the integral. This upper one becomes t instead of infinity, h of t minus tau, t tau. And then the bottom one actually becomes, and it's a little more easy to see, if h of t is 0 for all t less than 0, we've got h of tau right here. So this is 0 for all tau less than 0. So in the second interval, our lower limit becomes 0, h of tau, x of t minus tau, tau. And then similarly, if x of t is causal, if it's a causal input, you can also change the other limits. This would go then from 0 to t, and then from 0 to t again. So we're going to look at evaluating that interval. Look at what that means mathematically. I'm going to try and draw some pictures of what each of those terms looks like, and then break that down. Okay. Y of t is a function, it's the interval of the product of these two functions. X actually is a function of tau, if we look at the first integral. And then what's going on here with h with respect to tau, it's time reversed with respect to tau, and then shifted to t, to the location t. And y of t then is a function of that time shift in h of t. So I think the best way to kind of illustrate what's going on is we'll try to work through a couple of examples today. And so let's say x of t looks like this. Okay. It's 0 for all t less than 0. It is a causal function, but that doesn't really matter here. It's also 0 for all t greater than 1. And this is a fairly complicated impulse response. 0, 1, 2. And it has a height of 2. This is h of t. Now, we actually, our tau is our dummy integration variable here. So we want to redraw these as a function of tau. Now, my recommendation, you're always going to have two functions. In the integram, we've kind of got to time reverse and shift one of the functions. I find it always easier to time reverse and shift the simpler of the two functions. In this case, x of t is a simpler function than h of t. Doesn't matter, we could time reverse and shift h of t and we would get the same final answer. Okay? But so that's just a rule of thumb, time reverse and shift x of t. Okay. So we're going to actually evaluate minus infinity to infinity, the second form, h of tau, x of t minus tau, e tau. Now the first part of this is really easy. I'm going to sketch these two functions, h of tau and x of t minus tau. T is the variable, tau is my integration variable. Sketching h of tau is simple. That's just a change of variables. So h of tau looks just like h of t. It's the same function. It's just relabeling my axis. But that's in this integrand, okay, inside this integral. Now, what does x of t minus tau looks like? Well, I'm going to tell you what it looks like, and then we'll verify it. Okay. It's time reversed, and then the leading edge is shifted to t, location t. So now we start typically, and the first picture I'll draw, t is a negative value. So this is x of t minus. Since this thing has a width of 1, if this leading edge is at t, then this trailing edge is at t minus 1. Now you can't really tell the thing is time reversed here because it's symmetric, right? So the front edge looks just like the trailing edge. But it's time reversed, it's actually this edge that maps here, and then this edge that's at t equal 1 maps to t minus 1 here. Now again, we can verify this. This is a function of tau. When tau is equal to t, that's this point, when tau is equal to t, this is x of 0. So this edge corresponds to x of 0. When tau is equal to t minus 1, we've got t minus 1, that's x of 1, which is this edge. But now what I have to do when I'm evaluating this integral, I have to evaluate this for all possible values of t. So what this thing is doing as a function of t, as t is increasing, this block is sliding across here. Okay. I have to evaluate this at t equal minus 10, at t equal minus 8, t equal 12, t equal 1,000, all possible values. I have to draw that picture, but there are just some special cases that we look for. I can't do that for all possible values of t between minus infinity and infinity. But, okay, I want the product of these two functions. As long as t is negative, like I've drawn it in this first picture, what is the product of these two functions equal to? At every value of tau. So, I mean, if you were to take the product of two functions, and if you got the graphs of them, you just point by point, right? Multiply them together. Notice that for at least t less than 0, when this function is non-zero, this function is 0. So the product is going to be 0 everywhere. Okay. So I wasn't trying to trick you, but for all t less than 0, the integrand is 0, so the integral will be 0, and so the output will be 0. Okay. Now that's consistent with, now h of t as I've drawn it here is not the response to x of t, that's what we're trying to find. H of t is the response to an impulse. We're trying to find the response to x of t. But notice that x of t doesn't become non-zero until t equals 0, so we wouldn't expect any output for t less than 0. So that's this picture. Okay, so we've kind of done that part. I'm going to waste a lot of whiteboard. H of tau. And then the next picture I'm going to draw is when that leading edge is between 0 and 1. Okay. This is still x of t minus tau. This is tau. Okay. I'll need a mathematical expression for this. This actually has a slope of 2, right? So it's just 2 tau. Okay. This would have been, 2t. What is this? This is going to be minus 2, t minus 2, 2 minus t. So 2. So at t equal 1, at t equal 1, it's minus 1, so that'd be 2, or it's 2 times 2 minus t is probably a simpler way to write it. At t equal to 2, it's 0. At t equal to 1, it's 2. So that's the equation for that backside. Or over here in tau, this is 2 times 2 minus tau. Is that right? I think that's right. matches at the endpoints. That's the equation of the line. You could use your whole slope intercept stuff you learned in high school if you wanted. I was just trying to guess at it. Okay, so what does the product, so in the next region I'm considering is, I should have written this down, is now t is between 0 and 1. Now when t gets greater than 1, why I have that upper limit, that's where I've got a change in my h of tau function. So something different is going to happen there. But for t between 0 and 1, certainly as t moves to the right, you know, the picture I get is changing a little bit, but the functional form is the same. Okay? And that's what makes these problems difficult is, you know, what regions do I need to break the problem down into? When does the functional form of the product change? Okay. What is the product, though, for tau less than 0? It's going to be 0 because h of tau is 0 for tau less than 0, right? It doesn't matter that I've got something here. And when you multiply two functions, we do it point by point. This is 0, so this is 0. So the product is 0. What is the product for tau greater than t? And t is a variable here, but what's the product equal for tau greater than t? Well, this function is 0. So again, the product is going to be 0. I've only got a non-zero product where there's overlap between those two functions, where both of them are non-zero. Okay. And this was 2, right? Now, in that interval between, for tau between 0 and t, this is equal to the constant 2. That's equal to 2 tau. So that product is going to be 4 tau. That's the equation of that line there. You know, if this were a function of tau, you know, like maybe equal to tau, then I'd get 2 tau squared or something like that. But this is the product of those. And now what happens as t increases? This little triangle gets larger and larger, right? As t becomes smaller, as it goes towards 0, that little triangle becomes 0. It gets smaller and smaller, has smaller and smaller area, right? But this is the general picture I'll have as long as t is between 0 and 1. As soon as t is greater than 1, you know, I'm going to get that peak in there. Okay. So this is the h of tau, x of t minus tau product in this interval for t between 0 and 1. We have to, the next step is integrate over that product. That's simply finding the area. We can do it using the integral. Here it would be, the limits on my integration, though, are from 0 to t. I mean, they're from minus infinity to infinity, but the product is 0 everywhere except between 0 and t. So my limits on my integration are 0 to t. I know the product in that interval is 4 tau. I integrate with respect to tau. So what's that? 2 tau squared evaluated at 0 and t. So I get 2t squared. Any questions on that? What's the area of a triangle? 1/2 the base times the height, right? 1/2 of t times 4 tau squared. Actually, so this would be, at this point, this is the equation of the line. The height right here is actually 4t, right? So the width is t, that height is 4t, so it'd be 1/2 of 4t squared, or 2t squared. So you can do it just by calculating the area of the triangle. So here's what we have so far. 0 for t less than 0, and it's 2t squared for 0 less than t less than 1. Now, let's do this next interval where I think where t is between 1 and 2. And so my pictures are 0, 1, 2. This has a height of 2. This is h of tau. This is 2 tau. This is 2 times 2 minus tau.
I thought it was the very top one.
My x of t minus tau function. T is now here between 1 and 2. T minus 1 would then be between 0 and 1. This is t minus 1. This has a height of 2. This is tau. I'm going to give you a minute to sketch. Doesn't have to be exact, but roughly what the shape of h of t times x of t minus tau is. What I'm particularly interested in is, where is that product non-zero? Because that's going to determine the limits on my integration. So it looks something like that, right? Depending on where, if t is equal to 1, I really get the first half of this. With t equal to 2, I get that second half of that triangle. With t between 1 and 2, though, that product is going to look like that. I've got a constant times that shape, right? So I've kind of drawn that. Is that okay? This would have, the equation here would be 4 tau. This equation would be 4 times 2 minus tau. Questions there? Yeah.
So for like times between 1 and 2, then you start at like half and go to 1.5. Isn't h of tau the one like right at the peak of it?
So you're saying if t is what? If t is
1, wouldn't that be at the very peak of it?
It would be. And then, so this thing is pulling out a portion of this. So when t is 1, it's this triangle.
Yeah, but then you put your time interval from 1 to 2.
I did, what did I say I was going to do? I already did the 0 to 1 case, right?
Yeah. But your h of tau, it looks like it starts at a half, not 1.
H of tau starts at
Like where you're taking your measurement from?
Okay, that's the t minus 1 line, right? If t is between 1 and 2, the trailing edge is going to be between 0 and 1.
Okay.
Okay. So if this is at 1.5, this would be at a half.
Okay.
But this thing is really got to think. This picture is changing.
Yeah.
With t equal to 0, I'm sorry, with t equal to 1 and this equal to 0, it's going to pull out the first half of the picture.
Okay.
And then it's going to pull out that peak as t then moves up to 2. Okay, so this picture changes. The peak is going to be at a different spot there. The peak is always at the same spot, but the shape I pull out, the product will look different. So this is a little tougher to integrate because actually the functional form changes here of the product. So what I'd have to do is actually break my integral, going from minus infinity to infinity, finding the area of that. And you could use geometry to do that if you wanted to. I'll just formally carry out the integration. It would be an integral from t minus 1 to what is this point? Oh, that's always 2. That's always 1. That's the peak is always at tau equal 1. So it's going to be from t minus 1 to 1, and then 4 tau d tau. That's the area of this segment, plus the integral from 1 to t of 4 times 2 minus tau d tau. Right, I had to break the integral up because the functional form of the product changes as tau goes from for tau less than 1 and tau greater than 1. They're pretty simple integrals. So let me I'll have y of t here. This is 2 tau squared evaluated at t minus 1 and 1, plus this is going to be what? 2 tau minus 1/2 tau squared at 1 and t. Did I do that right? Does that look okay? And this is going to be messy. At 1, I'll keep the 2 out, but tau squared at 1 is 1, and then I have minus t minus 1 squared. So that'll simplify a little bit. Okay. And then this is going to be 2t minus 1/2 t squared, evaluating this at tau equal to t minus 2 minus 1/2, right? Minus 3/2. It's going to be that term. So, let's see. This is 1 minus t squared. I have minus 2t, so plus 2t plus 1 minus 1 plus, if I multiply the 4 through, we get 8t minus 2t squared minus 6. So finally trying to combine these, I've got a minus 2t squared minus 2t squared minus 4t squared. And that takes care of the t squared terms. Here I've got a 1 minus 1. I'll just get rid of both of those. And I've got a 4t plus an 8t, 12t. And then the only constant term I have left is 6. Y of t. So if I've done all that right, plus 12t minus 6, this is for t between 1 and 2. Unfortunately, I'm not done yet. I've got another picture for t between 2 and 3. That's where the trailing edge, the t minus 1, is between 1 and 2. So what that picture is going to look like. So this is for t between 2 and 3. So this is h of tau. 0, 1, 2. And x of t minus tau then. 2, 3. That leading edge is between 2 and 3. This is t. This is t minus 1. And this is the height of 2. And this equation was 2 times 2 minus tau. And what's difficult here, or what's really gets you to thinking about integration, is typically that when you do integrals, I think in calculus, the result is not a function of a variable. You integrate over something to find the area. Here you're finding the area, but it's of a function that's changing with time. And that forces you to look at this, I think a little deeper. Now, h of tau, x of t minus tau. When we get done here, I'll show you a little trick that'll help you to verify that these results are correct. I hope they are, but there's a check you can do to verify that. Will give us some confidence. So here we're only non-zero between t minus 1 and 2, right? Because above 2, for tau above 2, h of tau is 0. And below, for tau less than t minus 1, x of t minus tau is 0. So this thing is sliding across here. Right now I've kind of drawn that little triangle. As it continues to move to the right, this area gets smaller and smaller. And the height here, tau is equal to t minus 1. So this is 2 times 2 minus t minus 1 is that height, or 2 times, that's 3 minus t. 2 minus t. I think that's right. That height do that right at tau equal to 2, that should be 0. Tau at so t equal to 3. Yeah. So at t equal to 3, that's when this goes to 0. T minus 1 would be at 2. So I think that's right. So we'll actually get the area here just by finding the area of the triangle. So y of t in this interval, we're almost done. Hang in there. The width is 2 minus t minus 1. The height is 2 times 3 minus t, and then I'm going to take 1/2 that. I did that right. Okay. So fortunately that will cancel. This becomes 3 minus t times 3 minus t, or 3 minus t squared. For t greater than 3, what's the product? Yeah, for t greater than 3, this thing is now shifted beyond. My pulse is sliding across. For t greater than z3, the product is 0. So we're back to 0 for t greater than 3. So if we've done all this right, if we build a circuit that had this impulse response, this h of t, and we fed it this rectangular pulse here, that's the mathematical expression for the output. Now there's a couple different things that we can do here. One is, it'd be nice to kind of graph what that output looks like. One, two, three. Okay, so between 0 and 1, it's 2t squared. So at 0, it's 0. At 1, it's going to be 1, 2, 3. At 1, it's going to be 2, but it's 2t squared. That's what that would look like. Okay. Oops, I'm going to make it go up to 2. 2 is right here. So 2t squared between 0 and 1. Now between 1 and 2, it's this other shape, but let me at least check what it is at the input, at the endpoints. If I evaluate this at t equal to 1, I get minus 4 plus 12, that's 8, minus 6 is 2. So it matches up at that point. It's got that same endpoint. And this is a check on whether we've done the math correct. At these transition points, as we go to these different functional forms, they should always meet. There should never be a jump, okay, either up or down. The reason is we're doing an integration, which is a smoothing process. The only time we'll ever have jumps is if there are actual impulses in either one of these functions. Any other time, they'll actually match up. Okay. And then at 2, what's this become? This becomes 4 times 4 minus 16 plus 24. That's 8 minus 6, back to 2 again. So at 2, I think that curve does something like this. Okay. Between 2 and 3, if we check it at 2, oh, no, it looks like I messed up. So 3 minus 2 is 1, 1 squared is 1. Which would mean here, so I messed up here. I could have messed up the other one, but since it matches at this endpoint, I'm guessing I messed up here somewhere. Someone see my math error. That looks okay, doesn't it? 2, that width is 2 minus t minus 1 times this is 2, 3 minus t times a half. It's almost also 3 minus t.
Wouldn't that be t plus 3?
Here,
The first one?
here,
The 2 minus 1, wouldn't that be?
now if I multiply like the minus 1 through, that'd still be minus t plus 1. Well, it is back to 0 though at t minus 3. Based on the symmetry, well, I can check my notes. So what I have is 14 squared plus 12t. I had that. And somewhere, yeah, I messed up the last one. Oh, that's what I forgot to do. 2 times 2 should have been 4. So that's where I screwed up. So that means this should have actually been a 2 here, right? And finally, another 2 there. So now, at least at t equal to 2, this is 1 squared, or 1 times 2. So it matches up here. And at t equal to 3, it does that. And 0 for all. Now I'm back to y of t. A couple of things here. This has been a lot of work. Right? It's not been easy. There are numerous points at which you can make errors. I encourage you guys to get together and work together on these problems. Notice the width of this thing, the duration of this thing is 3. Now going back over here, the duration of my impulse response was 2. Now remember, this is the response to just a single impulse. So if I could think of x of t as, a bunch of impulses, an impulse, an impulse, an impulse, an impulse, an impulse, an impulse, one right after another for 1 second, and then they just go away. Now, in response to the impulse at 0, I get something that lasts for 2 seconds. In response to the impulse at 1, I get something that lasts for 2 seconds after this impulse at 1. So the duration of my result should be the width of these 2 durations. The duration should be 1 plus 2. So if we're dealing with finite width pulses, that's not always the case. I mean, this could be a unit step, which has infinite width, and then the output would have infinite width. But in this case, this has width 1, this has width 2, so the result has width 3. And it does. That's another check. You want to check at the inputs, at the end points, these transition points. That's how we found that error. Okay, that's always a good check. The other thing is, can we write this in some other form? You could. We could write the 2t squared as this is times a pulse of width 1, right? And then we could write it as minus 4t squared plus 12t minus 6 times another width u of t minus 1 minus u of t minus 2, and so on and so forth. And then times another pulse that goes from 2 to 3. We can actually combine some terms here because you'll have this times u of t minus 1. You've got a u of t minus 1 times that. So it simplifies. There's some algebra to simplify it. But you get a 1-line expression involving step functions, shifted step functions, and time polynomials. Okay, so you get 1 mathematical expression to represent the output, which makes it easier to graph in Octave or MATLAB. We could also, didn't have time to do this, and we will do this. We'll set up some circuits, have a given impulse response, and show you that we can mathematically calculate the output using convolution, and then we can verify that using LT space. All right, that's it.
for tomorrow. The eggs and eggs.
We have 3 seconds.